Welcome to the MOOCs course Advanced Thermodynamics. The title of this lecture is Liquid Mixtures and Excess Functions. Till now we have been discussing different aspects of fugacities, especially fugacities of gaseous mixtures when these gaseous mixtures obey the non-ideality. How the fugacity of that particular component can be estimated depending on the equation of state that has been used to describe the particular gas component or mixture of gaseous components. Right, those things we have seen, right, and then we have also seen what are the reasons for the non-ideality in the case of a gaseous mixture. So, what are those kind of forces, intermolecular forces that are causing some amount of non-ideality, and then how to make use of those intermolecular forces in order to describe the non-ideality of the system, and then from there how to get the fugacity of those non-ideal gaseous mixtures. Those things we have seen till now in last few lectures, right. Now we will be discussing fugacity of liquid mixtures. Okay. So, definition of fugacity in terms of chemical potential that we have derived at the beginning of this course is that mu I minus mu I naught is equals to RT ln Fi by Fi naught, right. Fi is the fugacity of that particular component in the mixture, Fi naught is the fugacity of that particular component as under certain specified reference states, or mu I naught is the chemical potential at the reference standard state. Okay. This superscript naught stands for reference state, that is what we have seen, and then this equation is useful only when we have the information about this Fi naught. So, for this, in order to know this Fi naught, what we need to have? We need to have a kind of some reference state, right. So, that reference state cannot be taken as blindly. So, what we have taken in the case of gaseous mixture, we know that for the gaseous mixture, if P tends to 0, the gaseous mixture reduces to the ideal gas mixture. If it is a pure component, then also when P tends to 0, the pure gas component reduces to ideal gas. Okay. So, that condition we have taken as a kind of reference, and then that reference standard state that we have taken Fi naught is equals to P if it is a pure component, that is the total pressure of the system, and then it is YIP, that is the partial pressure if it is a kind of a mixture of gases, that is what we have taken reference state, right. And then here this ideal gas behavior, that is what we have taken as a kind of reference state in the case of gaseous component. So, that what it tells that there is no intermolecular interactions or intermolecular potential, whatever gamma ij, those things we have seen, that is 0 for the ideal gas behavior, right. But that reference state we cannot take in the case of liquid mixtures, because the liquid mixture or any condensed phase is existing because of the presence of intermolecular forces. These intermolecular forces are binding the molecules together to form a kind of condensed phase. So, we cannot take a kind of limiting condition, no intermolecular potential as a kind of limiting condition, as a kind of or as a kind of reference state for the case of liquid solutions, right. And until and unless you have some information about this Fi naught, you cannot move forward to get more information about the fugacity of liquid mixtures, especially if these liquid mixtures are non-ideal. Okay. So, now those things we are going to see. First, what we do? We define ideal solutions in the context or in an analogous way to the ideal gases, and then we find out what is this Fi naught for ideal solutions, and then is it only one reference state possible, like in case of gaseous mixture, or more than one reference states are possible. Those things we see for these liquid solutions, and then we try to get more details about the macroscopic details, like how this non-ideality in the liquid phase may be related to the temperature, pressure and composition of that particular system. Those details we see and then we develop corresponding mathematical relations. So, here this naught refers to the standard state. For gases, it can be ideal gas state, as we have already seen several cases in previous few lectures. But what should be the reference state for the liquid solutions? Because in the if you take the ideal gas state, you are saying that intermolecular potential is 0, but in the case of liquid solutions you cannot say that this is intermolecular potential is 0, you cannot say that intermolecular potential is 0. So, then obviously this particular reference state, ideal gas reference state, whatever we have taken, that we cannot apply for the liquid solutions, and then there is no single suitable choice of reference state for liquid phase, right. So, what are those choices are available? Why not one single suitable choice of reference state is there for liquid phase? Why there are more than one reference states are available? Those things we have to see. Okay. So, in general there are two common reference states, that is, one is known as the Lewis-Randall rule or the ideal behavior with reference to the Lewis-Randall rule, and then ideal behavior with reference to the Henry's law. Okay. So, these details also we are going to see before getting information about what is FIL, fugacity of the component I in a liquid mixture, right. So, before going into these details we need to understand all these ideal solutions and then what are the reference states. So, ideal gas versus ideal solutions. What we do? We define ideal solution analogous to the ideal gas behavior. What we have in ideal gas behavior? In ideal gas behavior we say that there is no intermolecular interaction amongst the molecules of the gas whatever we have taken if it is ideal gas, or intermolecular potential is 0, that is what we say. But in the case of ideal solutions there are definitely intermolecular interactions, because of that one only indeed the solution condensed phase either in the liquid form or solid form it is possible. So, we cannot say there is no intermolecular potential, but what we can say that if the intermolecular interactions are same or intermolecular potentials are same for a given component, then we can say that particular component is a kind of a ideal component. Okay. Because we cannot say there is no intermolecular interaction, there is a definitely intermolecular interactions. So, what we can say, if these intermolecular interactions are same for all the molecules that are present in the system, then we can say that that particular liquid system is a kind of ideal liquid solution. Okay. For liquids, one cannot extrapolate ideal gas law to state that there are no intermolecular interactions, because presence of intermolecular forces makes these condensed phases to exist. And on macroscopic level we can say a solution is ideal when all mixing rules are same as for an ideal gas. For ideal gas what we have, delta V mix should be 0 and then delta H mix should also be 0, that is what we have seen. If these two principles are also applicable for liquid solution, then we can say those liquid solutions are also ideal liquid solutions, right. Now, though this ideal solution we are defining by taking ideal gas as a kind of reference, there are a few differences. One, what are those differences? That is what we see now, right. In the case of gases, if the gas is a pure gas, then also non-ideality is possible, right. In the case of gases, non-ideality is there because of increasing the pressure. When increases the pressure, the intermolecular interactions increases and there comes into the picture non-ideality, right. But in the case of liquid solutions, if the component is pure or the liquid component is pure, then all the interactions are same. So, let us say if you have a component A and then let us designate the molecules of that component A are like A like this. So, then for this molecule there are interactions and all these interactions are A interactions, that is all interactions are same. So, that means if you have a kind of pure liquid, then it will always be a kind of a ideal solution, because ideal solution says all the intermolecular interactions are same, right. And if in a system, if all the molecules are of the same substance, pure substance, then obviously all of their interactions would be same, whatever may be the pressure, low pressure or high pressure, whatever may be the pressure range, as long as that phase exists in a kind of liquid phase, all the interactions would be same. So, then that pure liquid will always be ideal, whereas a pure gas cannot be ideal always, whether the pure gas or mixture of gas, it can be ideal only at the low pressure. So, that is one of the difference. The first difference is this one, a pure gas can be non-ideal gas, but a pure liquid cannot be non-ideal solution, because if intermolecular forces are same, then we say that particular liquid solution has a kind of ideal liquid solution, right. So, if the liquid is pure liquid, obviously all the intermolecular forces would be same. So, then a pure liquid will always be ideal liquid, whereas a pure gas cannot be ideal always. A gas can be ideal only under the case of P tends to 0 or low pressure conditions. Okay. In the case of gases, increase in pressure leads to the deviation from the ideal gas behavior, because when you increase the pressure, the intermolecular interactions increases, the molecules come closer to each other, and then there will be interactions, and then depending on the nature of the interactions, different types of non-ideality may come into the picture for the case of gases, and those non-idealities may be represented by different equation of state. Those things we have seen. But in the case of liquids, it is not true, because in the case of liquids, whatever the non-ideality is there, that is coming because of the dissimilarity of the chemical nature of substance. That is, if you have a kind of A component, capital A component, which is having small a molecules. So, as long as this A is pure, all the interactions are same, whether you increase the pressure or decrease the pressure, it is not going to affect as long as this particular A component is in the liquid phase, right. But it can become non-ideal provided if you add some other component B. Let us say if you add some other component B, then there will be a kind of BB molecules will be there, and there will be a kind of interactions, AA interactions, BB interactions, and then AB interactions. Depending on the composition and depending on the nature of these interactions, the non-ideality may be coming into the picture. That is because of the change in composition, non-ideality is coming into the picture in the case of the solutions, okay, right. And then sometimes even these AB interactions, AA interactions are like interactions, BB interactions are also known as the like interactions, AB interactions are known as the unlike interaction, or the interaction between two different molecules. Okay. So, two different molecules does not mean that they always need to be different from the AA interactions and BB interactions. That means, even if there is a kind of solution, it is possible that this depending on the nature of this species, chemical nature of these molecules, if the AB interactions are also similar to either AA interactions or BB interactions, so then under such conditions this solution may also have a kind of some ideality under certain limiting conditions, something like Xi tends to 0 or Xi tends to 1 under those limiting conditions. Those things we will also see now anyway. So, increase in pressure leads to deviation from ideal gas behavior, whereas deviation from ideal solution are caused due to changes in composition, because non-ideal behavior results primarily from chemical differences of species in a mixture even at low pressures, provided that phase is in a kind of liquid phase, provided that phase is a liquid phase. So, now we have to define what is this fugacity of component I in the liquid phase. We have defined what is this Fi naught or the possible reference states. We are going to see more definitions anyway, right. So, now we have to define this FIL analogous to the case of ideal gases. So, mu I minus mu I naught is equals to RT ln Fi by Fi naught is equals to RT ln Yi. This is what we have already seen if the gaseous mixture is a kind of ideal gas mixture. Now, if you have a ideal liquid solution, then similarly what we can have? We have this relation mu I minus mu I naught is equals to RT ln Fi by Fi naught, and then superscript L we are using to distinguish for the liquid phase. This is the same whether it is condensed phase or gaseous phase, this relation is same, it is not going to change, okay. But only thing that whether it is appropriate to use or not, that depends on the case to case and then depends on the data availability, those things we will see anyway, right. So, this is same. So, here also for the gases, ideal gases, up to this part is same, right. So, now if the gas is ideal gas, then this difference is nothing but RT ln Yi. So, similarly analogously if you wanted to define for the ideal solutions, this difference, that is mu I minus mu I naught, you should define is at you should define it as RT ln Xi, where Xi is nothing but the mole fraction of that particular component I in the liquid solution, right. So, that means what we can write from here, we can write that FIL is nothing but, by equating these two, we can write FIL is nothing but Xi Fi naught Xi Fi naught, this is what we can write. So, now here this Fi naught is at certain reference standard state. This equation is useful only when we know what is this Fi naught, okay, that we see anyway by taking different reference state. So, this is for the ideal solution. If the solution, liquid solution is ideal, then FIL is equals to Xi Fi naught, or we can say FIL is proportional to Xi if it is ideal solution. Linear relationship is there, and then that constant, proportionality constant is Fi naught for the time being. It can be different also depending on what reference state are we taking, right. So, non-ideality in the system or the non-ideal liquid solution behavior brings in the activity coefficient as correction, like FIV in the vapor phase or the gaseous phase, what we have Yi P Phi, this is what we are having, or if you have not defined as a kind of any reference state, then you have Yi Fi naught Phi, this is what you have for the vapor phase. So, this composition is there, and then this reference state at certain reference state, what is Fi naught, that is there. So, additionally this Figasty coefficient Phi is there in the case of gases or vapor mixtures. So, analogously if you write for the liquid states, then it should be in place of Yi it should be Xi, and then Fi naught some reference state, at some reference state what is the Figasty, that we do not know, we are writing Fi naught, and then non-ideality in the vapor phase is brought into the picture in terms of this Phi. So, now here the same thing, non-ideality in the liquid phase is brought into the picture by this activity coefficient gamma I. So, FIL is equals to gamma I Xi Fi naught. So, this gamma I whatever is there, that is known as the activity coefficient, it brings in the non-ideality in the system, or it brings in the effect of non-ideality in the system. Okay. Whatever the non-ideality is there in that system, that can be mathematically represented or related to the Figasity through this activity coefficient gamma I, right. So, as we have seen, in the case of ideal solution, the intermolecular force is not 0, but same for all molecules of solutions, right. So, this is the difference between ideal gas and then ideal solution. Ideal gas, we are saying there are no intermolecular forces at all. In the ideal solution, we are saying there are intermolecular forces, indeed there exist intermolecular forces, that is the reason this condensed phase is existing, but we can say this liquid or solution phase as a kind of ideal if these intermolecular forces are same in a given system. Okay. So, now reference states for the liquid phase. Okay. So, now what we do before going into the details of reference state, we take a binary mixture of component A and then component B. This A is having molecules AA molecules, and then B is having BB molecules, like this. What we do, this liquid mixture A and B we take, then we experimentally measure the Figasty of component A in this liquid mixture, and then for different composition this Figasty of liquid mixture, this Figasty of A in the liquid mixture we measure, and that information, that is FAL versus XA, FAL versus XA we plot experimentally whatever the information is there. Let us say that information is having this particular nature. This FAL versus XA, if you plot experimental information whatever is there, that is having this solid curve like this, right, and then two limits of XA are 0 and then 1, we can see FAL versus XA is non-linear because there is a kind of non-ideality. If at all it is ideal, then we should have this FAL is equals to some reference state Fi or now component A Fa naught multiplied by XA. This form we should have if it is an ideal solution, but it is not ideal. So, that is the reason we are having non-ideal nature of the curve like this, right. So, now what we do, we take the either extremes of XA. Let us start with XA tends to 1. Then what we have in the system only AA molecules are there, because XA tends to 1, that means it is almost pure component 1, right. Only a few B molecules are there and they are negligible compared to the A molecule. So, any A molecule if you take with reference to this A molecule, what it sees in its neighborhood, it will see only AA molecules, right, because they are only majorly dominating. So, under such conditions what we will have? We will be having AA interactions, and in all these AA interactions are equal, right. So, that means and XA tends to 1, then XB tends to 0. So, XA tends to 1, that means a kind of pure component 1 or pure component A, right. If the pure component, if the liquid component is pure component, then obviously it is ideal component. So, that is the reason in the limit close to XA tends to 1, in the limit close to XA tends to 1, we can see a kind of a linear behavior is there, right. So, that means obviously whatever this reference state Fa naught is there, that should be F pure A or Fa pure, anyway you can write it. So, this is one of the reference states, right. Okay. And now, this particular case where XA tends to 1, mostly A interactions are there, all those interactions are same. So, then we have a kind of ideal behavior in the limit XA tends to 1. So, this is one boundary condition or one limiting condition of XA, because XA tends to 0 to 1, right. So, whatever this XA tends to 1, then fugacity of that particular component should be equals to fugacity of pure component. So, that means Fa naught you can take Fa pure 1 or pure F pure A, that is what you can say, right. So, that is one reference state, and this known as the Lewis-Randall rule, right. And then this whatever this line is there, this limit XA tends to 1, this straight line if you extend further. So, you have this particular line, then you can say F ideal is equals to Fa ideal is equals to XA Fa pure A, or the fugacity of pure component A multiplied by XA should be equals to Fa ideal. If you define Lewis-Randall rule as a kind of reference state, then you will have this one. Okay. Other limitation is XA tends to 0, that means A is present in very small quantities. You can see here now A is present in very small quantities in B, that is it dilute solution of A, right. Now, here you can see with reference to A, we are doing all these things with reference to A. So, with reference to A, it will see only AB interactions, right. So, it will have only AB interactions. So, all these AB interactions are also equal, similar with reference to A. So, under such condition also it is ideal. Ideal in the sense all the interactions should be same, or intermolecular forces should be same. So, intermolecular forces now we are representing qualitatively in terms of interactions. So, in the case of Lewis-Randall law, all interactions are same, but those interactions are AA. In the case of other limitation XA tends to 0, all interactions are again same, but those interactions are AB interactions. So, under this limitation also we can have for certain range a kind of ideal behavior. That is the reason here again we have a kind of a linear curve for the range, when XA tends to 0. and this case whatever the Fa ideal is there. So, that can be referred or defined with respect to Henry's law as a kind of a reference state. Henry's law can be taken as a kind of reference state, and under such conditions whatever the Fi naught or Fa naught is there in this case is nothing but Ha, that is Henry's law constant. So, now we have two reference states for liquid solutions. When Xa tends to 1, whatever the Fa naught is nothing but F pure A or Fa pure, and then another limiting condition Xa tends to 0, where we can have Fa naught is equals to Henry's law constant Ha, right. So, there may be a case, indeed there should be a case where the reference state may be valid for the entire range of Xa from 0 to 1, right. So, then under such conditions this Fa naught should be Xa F pure A or Fa pure, Fa pure. This is what we have, and this is known as Raoult's law. So, if the solution is ideal in the entire range of mole fraction of A from 0 to 1, then that ideality may be defined with respect to the Raoult's law, where Fa is nothing but Xa Fa pure, and in many cases Fa pure is taken as the Pa sat or the saturation pressure of that component A, that way it has been taken. So, now we can see different reference states are possible in the case of a liquid phase. Okay. So, now what we have, we see a detail of these things, that is Figas, that is a kind of notes, everything is given here, alright. Figasti of A in liquid phase is plotted against its mole fraction for a binary system here. For either extremes, that is Xa tends to 0 and Xa tends to 1, this plot is linear, we can see here, right. So, as we have seen, and now we can see when Xa tends to 1 under the Lewis-Randall case, this Fa pure is a kind of reference state, whereas a kind of Xa tends to 0, then this Ha, that Henry's constant or Henry's law, according to Henry's law, whatever the Henry's constant Ha is there, that should be a kind of reference state or Fi naught or Fa naught in the case, right. Now, we can see here Fa pure is much small, whereas Ha is much large. What does it mean? If you see the Figasti as a kind of tendency to escape, right, tendency to escape and then join with the other molecules or get into the other phases, that is what it roughly means by, right. So, if the tendency is more, so then it is easily escaping and then going and joining with other molecules or other species or into the other phase is also possible, right. So, that is that under such conditions we can say that the non-ideality is very high, it is easily going and then joining with the other molecules. If tendency is low, that means it is having strong binding with its own molecules, and then it is not going to escape from this phase and then joining to the other phase or other species, right. So, smaller Figasti, that means stronger interactions, stronger like interaction, and then molecules try to be together themselves in their ideal state, in their own state as a kind of ideal state, right. So, if the tendency is high, that means let us say in the case of second case where Xa tends to 0, the molecules, A molecules are very few, and then it is not possible for it to stay with the B molecules comfortably. So, it will try to escape, its tendency to escape from the mixture of AB would be high, that is the reason Ha is high. Whereas, the other extreme Xa tends to 1, it is with reference to A molecules, all the molecules are A molecules kind of thing. So, it is having good binding with A molecule. So, it do not want to move from its own A molecules in the vicinity to the surrounding other molecules, are escaping from this liquid phase and then going and joining to the other molecules. So, that is the reason Fa pure is low, right. So, that means Fa pure is low, that means here the like interactions are very strong. If Ha is large, that means here unlike interactions are going to have a kind of are going to define the ideality, and then these A molecules are having higher tendency to escape from the solution. Okay. But in either of the extremes, what we have, FIL is equals to Xi Fi naught, that is linear plot is there. That means, if the plot between FIL and Xi is linear, then we can say that the mixture is a ideal liquid mixture. Okay. For Xi tends to 1, solution is almost completely containing A. Thus, A can fill essentially only other A species as it interacts with its neighbor. That means, we have ideal solution, because as far as molecules of species A concerned, all the intermolecular interactions are same, that is all are AA interactions. And characteristics of this intermolecular interaction is given by pure species fugacity Fa pure. So, under such conditions, Fa naught is nothing but Fa pure. So, accordingly, one choice of reference state is pure species fugacity of species A and is known as Lewis-Randall rule, and that is Xi tends to 1, Fi naught is equals to F pure I, where AA interactions are dominating, or all the interactions are AA kind of interactions and they are similar interactions. For the case when A is very dilute in B, then what we say, Xi tends to 0, because A is very small in B. In this case, as far as molecules of A concerned, they essentially seize only species B in the solution. Thus, again we have an ideal solution, because all intermolecular interactions species A has are the same again. But in the case these interactions are AB interaction, that is the characteristic of ideal solution in the limit of Xi tends to 0. Unlike in the case of Xi tends to 1, it is AA interactions. Whether it is AA interactions or AB interaction, it should be same, then we can say it is ideal solution. So, in the case of Xi tends to 0, it is AB interaction that are there, and then they are all same, especially with respect to A. This provides another choice of reference state based on AB interaction and is known as the Henry's law. So, that is for Xi tends to 0, Fi naught is equals to H high. H high is nothing but the Henry's law constant for that component I in a solvent, whichever solvent we have taken. So, in this case solvent is B. Henry's law limit can be conceptualized as a hypothetical pure fluid in which characteristic energy of interactions is between A and B molecules only. So, now if A is defined by Lewis-Randall reference state, then it can be called as a kind of solvent, because Lewis-Randall reference state, that means pure component fugacity we are taking, pure component fugacity we are taking as a reference, that means Xi is going to be close to 1. So, in the case of Xi, here in the case of this one, it is Xi tends to 1, that means it is all pure solvent A is there is no B at all. But with respect to Henry's law, if you take, this A is present in only small quantities as a solute in B solvent, right. So, that is the difference. If A is defined by Lewis-Randall reference state, then it called as a kind of solvent, whereas if it is described by Henry's law, the same A is called as a kind of solute, because it is present in very minute small quantities. Xi tends to 0. It is not exactly 0, Xi tends to 0, small quantities. So, if we have a binary mixture of species A with different species C, then what will happen? So, the example that we have seen for the binary mixture of A and B. Now, again we take a binary mixture, but A and C, right. So, then reference states, how would they change? So, Xi tends to 1, it is pure A almost, whether the other component which is present in very small quantities, if it is B or C, it does not make difference. It does not make any difference. So, that Lewis Randall reference state is going to remain same, that is Fi naught is going to be F pure I, right. But in the case of Xi tends to 0, so it is now Xi tends to 0, that means Henry's law is a kind of reference state. So, then under such conditions what happens, this A is present in very small quantities, very small quantities, and then it is going to be mixed with some other solvent C, because now the binary mixture is A and C. Previously the binary mixture was A and B. So, in the case of A and C solution which is defined using the Henry's law, so this whatever the Fi naught is going to be very different compared to the in the previous case, because what Henry's law says, it defines about the solubility of a specific solute in a solvent. So, now solvent is changing though the solute is remaining. So, depending on the solubility of this solute A in B and then depending on the solubility of solute A in C, this reference state would dramatically change. If the solubility of A in B and C is almost same, then this may remain same. There is no guarantee that the solubility of solute A is going to be same in two different solvents. So, this Henry's law reference state is not going to be same if you change the solvent or if you change the second component of the binary mixture. Whereas, Lewis Randall reference state is going to be same, because whatever the Xi tends to 1, it sees only Xi tends to 1, what is the remaining small amount, that does not make any difference. So, it is going to be Fa pure I or Fa pure or F pure I. Okay. So, that is what we see now here. So, if you have a binary mixture of A and C, then Lewis Randall reference state for species A would be unchanged, obviously because of this reason. But Henry's law reference state could differ dramatically, because it depends on the solubility of A in B and then solubility of A and C. So, in general solubility of one solute in two different solvents may not be same. So, it may differ dramatically, because Lr is independent of any other species in the mixture, but Henry's law depends on the chemical nature of other species in the mixture in which the solute A is going to be dissolved to form a kind of a liquid solution. So, that means further another step, if Fi L is equals to Xi Fi naught holds for the entire range of composition, that is from Xi varying from 0 to 1, that is for the entire range, then the solution is ideal in the sense of Raoult's law, where we have Fi L is equals to F pure I multiplied by Xi, right. So, this Henry's law is applicable when Xi tends to 0, and then Lewis Randall rule is applicable when Xi tends to 1. But the ideal behavior is there for the entire range of Xi changing from 0 to 1, then this Raoult's law is going to be a kind of reference state, and then for that case this Fi L is defined as F pure I multiplied by Xi, and then for majority of the cases F pure I is defined as Pi sat, or saturation pressure of that component I. This F pure I is mostly defined or taken as Pi sat, or saturation pressure of that ith component. Okay. Now, we see fugacity of ideal solution. Okay. So, we have seen a few basic details of ideal solution that are required in order to get into the fugacity of a liquid solution. So, before going into the details of fugacity of non-ideal solutions, we start with fugacity of ideal solution, right. Ideal solution is one for which at constant temperature and pressure, fugacity of every component is proportional to some suitable measure of its concentration, usually mole fraction. That is what we have seen. So, that means Fi L is proportional to Xi, that we can write Fi L is equals to some constant Ri Xi, and then this Ri is going to change depending on the reference state, which reference state we are going to take. If you take Xi tends to 0, then it should be Hi, and then if you take Xi tends to 1, then it should be F pure I. That is what we have seen. So, this is Ri is a proportionality constant and it is independent of mole fraction or composition. Okay. So, by some means if we can put Fi naught is equals to Ri, then we can say gamma I is equals to 1, that means the ideal behavior gamma I or the activity coefficient should be 1. If the solution is ideal solution, then this gamma I has to be 1. Similarly, like if the gaseous mixture is ideal gas mixture, then figacity phi I should be equals to 1. That is how we have defined for the gaseous mixture. The similar way for the liquid mixture also, gamma I should be equals to 1 if the solution is ideal liquid solution. So, this equation 1 holds for the entire range of composition from xi is equals to 0 to 1, then the solution is ideal in the sense of Raoult's law. Remember, this definition is true for the ideal liquid solution only. This equation number 1 is true only for the ideal liquid solution only. If the liquid solution is non-ideal, then we have FIL is equals to some constant Ri xi, then gamma I. That activity coefficient, this gamma I is known as the activity coefficient that will come into the picture. For such ideal solution, from boundary condition at xi is equals to 1, then Ri is equals to F pure I at the same temperature of solution as we have already discussed previously. Then we can write F at constant temperature, pressure and composition xi should be equals to F pure I at constant temperature and pressure multiplied by mole fraction of that component I, that is xi. And then in many cases simple proportionality between FIL and xi holds over a small range of composition in general, right. So, if xi is near 0, then it is still possible to have an ideal solution according to equation number 1, whatever that FIL is equals to Ri xi. But if xi is equals to xi tends to 0, then you do not need to write Ri is equals to F pure I, but you have some other constant Hi according to Henry's law. Such a solution is called as an ideal solution leading to the familiar relation known as the Henry's law. Okay. So, in the case of xi tends to 0, this constant Ri is equals to Hi. In the case of xi tends to 1, this constant Ri is nothing but F pure I. The previous one we have discussed for only binary mixture A and B. Now, we are writing the same relation for a generalized case where it can be any number of components. So, now we see excess functions. What are these excess functions? Why should we define this excess function in order to discuss the non-ideality of liquid mixtures? That is what we are going to see now. Whatever the previous derivations are there, that is mu I minus mu I naught is equals to RT d ln Fi. This information we have derived in the beginning of the course, right. This information, this equation is defined irrespective of the phase, which phase are we dealing with. So, it is valid for all the phases, gaseous phase, liquid phase and solid phases also, right. So, these derivations of figacities from volumetric data are general and may be applied to condensed phase as well in addition to the gas phase. But however, though this equation we have used successfully for the case of gaseous mixtures, we may not able to use this expression for the condensed phase or liquid mixtures, because it is not practical to do, because necessary integrations require that this volumetric data should be available at constant temperature and in constant composition, but over the entire density range from ideal gas state, that is 0 density range, to the density of condensed phase, including two phase region if at all there is a two phase region existing. So, this information is required actually. Okay. So, and obtaining such data for fluid mixtures is very tedious and a very few data only available in the literature. Because of this reason, this equation we cannot use directly for the case of liquid solution. So, there must be an alternative approach for calculating Figasti's in liquid solutions, right. And one such method is obtained by defining an ideal liquid solution and by describing deviation from ideal behavior in terms of excess functions. Okay. In terms of excess functions. Excess functions, what does it mean by? Like, thermodynamic property of real solution minus the thermodynamic property of the ideal system at the same temperature, pressure and composition. That is in excess to the ideal solution conditions, whatever the thermodynamic property in excess to the ideal phase, ideal liquid solution conditions, but at the same temperature, pressure, composition. So, this may be helpful in getting the required activity coefficient. So, this excess function may provide us required activity coefficient that describe the non-ideality in the liquid solutions. Okay. So, how it is going to be useful, how this excess function is going to be useful to develop this activity coefficient relation for the case of a liquid solution, that is what we are going to see now. So, excess functions are thermodynamic properties of solution that are in excess of those of an ideal solution or ideal dilute solution at the same conditions of temperature, pressure and composition. That means, for ideal solutions all excess functions are 0. Excess function is nothing but, for example, excess Gibbs energy, if you defined excess Gibbs energy, the superscript E stands for excess. This excess Gibbs energy, total Gibbs energy is nothing but G actual solution at temperature, pressure and composition minus G ideal solution at same temperature, pressure and composition as of the actual solution. So, this part, second part in the RHS is refers to the ideal solution, but at the same temperature, pressure and composition, and then this is for the real solution or actual solution. Okay. If you take this difference, whatever excess is there, that is known as the excess thermodynamic property. Here in the case of in this case we have defined for the Gibbs energy. If it is 0, that means system is ideal, because whatever the property and the real conditions are there, they are same as the property under the ideal condition. So, that property is going to be, that excess property is going to be 0. So, that means for ideal solutions all excess functions are 0. Similar definitions are hold for the excess volume, excess entropy, excess enthalpy, etc. These relations in general we are having for thermodynamic properties, they are also valid for excess thermodynamic properties as well, right. And then partial derivatives are also similar for this excess function. For examples defined like this. Okay. So, excess functions can be positive deviation or negative deviation. So, partial excess functions are also defined analogously. Let us say if M is an extensive thermodynamic property, then Mi bar we have defined like this. So, similarly Mi bar E we can define like this, only thing that here now we are using Me, excess property, excess extensive property M, and then M is equals to sigma Ni Mi bar we have in general. So, in terms of excess properties, if you have, we can have Me is equals to sigma Ni Mi bar E. So, analogously we can define these properties without any difficulty for the case of excess functions as well. Activity coefficient tells us how active the liquid is relative to our choice of reference state, and then activity and an activity coefficient if you wanted to define. So, activity of component I Ai at Tpx is equivalently defined as ratio between Fi and then Fi naught. Fi is at Tpx, Fi naught is at Tp naught x naught. So, that is P naught and X naught are arbitrary, but specified pressure and specified composition. And then activity coefficient gamma I is defined as activity divided by the concentration. This A I is the activity and then gamma I is the activity coefficient. So, now here from here what we are having, A I is equals to F I by F I naught, and then from here A I is equals to gamma I X I, that is what we are having. So, that means if the system is ideal, then what we can say, A I is nothing but X I, that is activity of that particular component is equal to the is equals to the mole fraction of that particular component, provided that solution is ideal. Okay. This is going to be useful here in order to define the relation between excess Gibbs energy and activity coefficient. Okay. Now, we try to develop relation between excess Gibbs energy and activity coefficient. So, first we have to write excess Gibbs energy, but what we do, excess partial molar Gibbs energy we are writing, right. Excess partial molar Gibbs energy is nothing but partial molar Gibbs energy of that component I under the real conditions minus partial molar Gibbs energy of the same component under the ideal condition at the same temperature, pressure and composition as of the real solution, right. So, then this G I bar, we know that it is nothing but RT ln Fi real, by the definition already we have defined previously, and then G I bar ideal should be RT ln Fi ideal. That means, we can write G I bar E is nothing but RT ln Fi by Fi ideal. That means, let us say if you take some Ri as a kind of reference state, then Gi bar E is nothing but RT ln Fi by Ri Xi. This is what we have, right. Just now we have seen this Ai is equals to gamma I Xi, and then we have also seen that Ai is equals to Fi by some reference standard state Fi naught, right. Let us say if you have this ideal behavior, then FIL is equals to Ri Xi, linear relation should be there, and this if you take this ideal solution is one for which activity is equal to the molar fraction that we have seen already. If ideal solution, then activity is equal, activity coefficient is equals to 1. So, then activity is in nothing but molar fraction of that particular component, right. Then set the standard state Fi naught is equals to Ri, then what we can have? We can have Ai is equals to Fi by Ri. Now, this in place of Fi by Ri here, if you substitute gamma I Xi, then what we have? We have RT ln gamma I Xi divided by Xi. So, this Xi is cancelled out. So, then we can have RT ln gamma I. So, that is Gi bar is equals to RT ln gamma I. So, this is the most important relation that we wanted to develop, because now if you know the partial molar Gibbs energy, excess partial molar Gibbs energy of component I, you can find out its activity coefficient gamma I. If the activity coefficient is known, then you can establish the non-ideality in the liquid phase as well. So, this is going to be very much essential, and this relation must be remembered for long time, right. So, the same thing we can develop very simple way. So, we have this one, this relation. So, that is Gi bar is equals to RT ln Fi real by Fi ideal. Fi real is nothing but gamma I Xi Fi naught. What is this reference state? Let us not worry about it. And then Fi ideal is nothing but Xi Fi naught. Again, what is this reference state? Whether LR or Henry's law or Raoult's law, let us not worry. So, then here again Xi, Fi naught are cancelled out. So, you have RT ln gamma I. the same relation we can get this is the simpler way to get this same relation, that is Gi bar E is equals to RT ln gamma I. This is going to be very essential for next few lectures as long as we are going to deal with this liquid mixtures. So, molar excess Gibbs energy Ge is nothing but RT sigma Xi ln gamma I, because we have this Me is equals to sigma Ni Mi bar E. So, here Xi, if you write Ni by Nt, that Nt if you take to the left hand side, so Nt Ge, that will become capital Ge. Remember, our notations are same as we have been following in the entire course. Capital letters, total properties we are taking, small letters we are taking for the molar properties, small letters with bar we are taking for partial molar properties. In the case here now, G I have written because we are discussing Gibbs energy here. The same notations we are following here. So, relation between molar and partial molar excess Gibbs energy, we can have it as, we have this Ge is equals to RT sigma Xi ln gamma I. So, that means Xi if I write Ni by Nt. So, Nt if I take to the left hand side, Nt Ge is equals to RT sigma Ni ln gamma I. So, Gi bar E, if you wanted to know, you have to differentiate this left hand side with respect to Ni. That if you do, dou by dou Ni of Nt Ge is nothing but Gi bar. So, that is you will get RT ln gamma I multiplied by dou by dou Ni of Ni is 1 here. So, ln gamma I only you will be having plus sigma Nk dou ln gamma k by dou Ni Tp Nj for all remaining components, generalized we are writing. And then from Gibbs Duhem equation we can find it out, this summation which includes for the component I also is going to be 0. So, that means again we have this expression Gi bar is equals to RT ln gamma I. Different ways of getting the same expression, we are trying to get these things, right. So, this is going to be important, this is what we have developed. This expression now we will be taking as a kind of basis for developing next discussions in coming lectures. So, this Gi bar E is equals to RT ln gamma I. So, from here you can get the gamma I. So, that means if you know the Gibbs energy, excess Gibbs energy or molar excess Gibbs energy, if you know, then you can calculate this gamma I, and then once you have the gamma I, you can establish the non-ideality in the system. This is what we are going to do in the next coming up couple of lectures. So, the references for this particular lecture are given here: Engineering and Chemical Thermodynamics by Koretsky, Molecular Thermodynamics of Fluid Phase Equilibria by Prosnich et al., Chemical, Biochemical and Engineering Thermodynamics by Sandler, and Introduction to Chemical Engineering Thermodynamics by Smith et al. So, most of the lecture that we have discussed are taken from these two reference books, Koretsky and Prosnich et al. Thank you.